You're basically just restating what that says. There's no interpretation there. All right, now we found that S double prime at that value is greater than 0. Now that piece of information by itself, without taking into account any other piece of information, there's only one thing you could say with certainty about the graph at that point. And what is it? Parker?
It's concave up.
All right, so we got, the first part took longer than last period, the second part we got quicker, much quicker. This means that S is concave up at that point. Now, we're going to take those two pieces of information together, and they together tell us what's going on the graph of S at that point. Absolute minimum. Look, here's our horizontal tangent right here, okay? Horizontal tangent line and concave up at that point means there's an absolute minimum. Horizontal tangent and concave down, that's this. Absolute maximum. So we could say S has its minimum. It has no apostrophe. So
why can't those be local?
Because there's only one, and for it to be local, there'd have to be a change in concavity someplace. But we're only talking about what's at that point, and since it's the only one, and based on the behavior of the function, there's a whole bunch of things that factor into that. And we say has its minimum, that implies absolute minimum. Okay, if you say has a minimum, that implies local because of the article that you're using. When R equals a cube root of V divided by 2 pi. Okay, now we're going to go back and read the problem. So we're going to see if there's units of measure involved. There isn't. And we're going to hope that it doesn't ask for what the surface area is, because we don't want to have to substitute this value into the surface area equation. It says find the radius. All right, so we're done. There's no units either. Now, we want to talk about why we keep V as V. And say, why didn't they just give us a number? Why did they give us V? All right, because this right here, this relationship is going to work for any size can in any unit of measure. So, people think of engineers as people like, oh, they designed that bridge and whatever. Engineers do a lot of different things. And some of them, like, you ever open up a package, you're like, oh, it's really neat how they put that in there, and this is tucked in the corner, and that's underneath to minimize the amount of packaging. Because people do that also, and they're kind of the unsung heroes, because like the people who designed the iPhone, they get all the credit, but somebody else had to design the packaging, and that's part of the deal also. So by doing this, this person doesn't have to keep repeating the work. They know, well, if I have a can, and they give me the volume, I know what my radius should be in terms of volume. So this work never has to be repeated then. They could just take the volume, substitute it in, they know what the radius should be. Right? Because the work would be essentially the same, you just keep changing a number to whatever, oh, this can has to hold 12 cubic inches, and that one has to hold 30 cubic inches, and it'll work for cubic inches, cubic centimeters, cubic meters, any measurement. All right, so we kept it general so it can be generally applied. All right, so engineers do all sorts of different things. So when people tell me, oh, I want to be an engineer, I said, what type of engineer do you want to be? I was like, oh, I don't know. You want to be a civil engineer? So I knew somebody who was an engineer, and what she did is she had to figure out when they were building high rises where the best places to put the toilets were. So that, with the plumbing and everything, that it would be most efficient, and it would be, ergonomic in terms of access to people. Like you wouldn't have a huge floor and put the bathroom in the corner. And then somebody on that side's got to go really bad, and they got to go through all these offices, and they have an accident on the way. And then everybody at the water cooler is like, hey, did you hear about Tim? It's like, oh, no, what happened? It's like, yeah, he had an accident. And what kind of accident? You know. It's like, no, I don't. I don't want to say. Don't tell him I told you, but All right, so. All right, we're going to go back and talk about those problems from yesterday now. We're going to start with number 7. Okay, so transferring from 6 to 7, I want to talk about some observations I had, and there are observations from both classes as well. All right, the secondary equation isn't any different. I had people saying 4 equals 2x squared h. The volume's the same. If you have a top on the box or there's no top on the box, the volume's still the same, but the surface area changes because you need to take some of that material that you had and use it to make a top also. So that means taking a little bit off basically the other 5 bases so you can create a 6th base. All right. The primary equation is a little bit different because you have 2x squared, you have a top and a bottom instead of just a bottom. All right. The work is in essence the same. All right. Now, the big thing that people had difficulties with, people get problems going from x cubed equals 4 to x equals a cube root of 4, which you should be all right with, and that's simplified. You don't need a calculator for that. All right. But then the problem after that was people going over here and trying to substitute this. All right, which in both classes it was not good. Okay, it was kind of frustrating. All right. I had people that cubed the cube root of 4 and say, oh, cube root of 16. First off, that's not simplified, cube root of 16. But that's not the way to look at it. And I'm going to scroll up because I had to write the work up here, which really should be mental math. But you have to treat cube root of 4 as 4 to the 1/3, because if you're going to use properties of exponents, you want to have it written with an exponent, not a radical. So 4 to the 1/3 squared is 4 to the 2/3. We multiply the exponents together. And then 4 to the 1st divided by 4 to the 2/3, we do 1 minus 2/3, which that's why I was talking in the beginning of class about how I had people who struggled with 1 minus 2/3, which shouldn't be a problem. And I had to tell people to write it in a common denominator, which you have to understand, 1 minus 2/3, that's elementary level math also. That's not even middle school math. Right? Start doing common denominators maybe in 4th or 5th grade. All right, so you don't have to write which one's base and which one's the height because it's a cube. All right, I wrote to emphasize it, but let's say you had a different form, like if you had 4 divided by the cube root of 16. Now that is correct, but it's not simplified. And if you have a multiple choice question, 4 divided by the cube root of 16 is not going to be there. So that you're talking about getting like 98% of the way and then getting the problem wrong because your answer isn't there when you did all the calculus right and you got tripped up over some properties of exponents. Okay, so we need to make sure that we can execute those things. It's not enough just to do the calculus, because the calculus is actually a very small part of these problems. All right, number 4. All right, we're looking to maximize the product because it says whose product is as large as possible. So there's always going to be some read and interpret, called decoding, in any kind of word problem. And you have to set up equations. So product is x times y. We're not making a sketch here because we're not actually building something. Okay, so there's no sketch necessary. All right, here, it doesn't matter whether you solve for x or for y because it's equal levels of difficulty. If you solve for the other variable, you're just going to get the y first, and then you'll get the x instead of getting the x and getting the y. Now the domain, 0 less than x is less than 18, because not only does it say their sum is 18, but it says the numbers are positive. So x has to be greater than 0, but why does it have to be less than 18? If we made x equal to 18, what would y have to be? 0. What do we know about 0? It's not positive. So that's why we have to go strictly less than 18. Remember, for the feasible domain, you have to take into account the function, your primary equation, and the context of the problem. Okay? And then I wrote a sentence. You could have just said 9 and 9. That's it. Be done with it. Make sure this is all labeled here. Your sign test reflects a feasible domain. So if you have arrows without stopping at 18, and you're 0 to 18, your sign test isn't correct because it doesn't properly represent the domain. It's basically then, that would imply that you wrote the domain down and then didn't consider it in the rest of the problem. All right, number 5 is similar, but not the same. Okay, why don't I have a feasible domain here? Why is there nothing written? There's no restrictions on X and Y. In number 4, it said 2 positive numbers. Here it said 2 real numbers. Those numbers can wind up being anything. All right, so we said feasible domain is minimum and or maximum values if they exist. All right, and it's all situation specific. Something in the wording of the problem, the nature of the problem is going to tell you that, but you have to think, you have to decode. And that's why people struggle with this. Remember I said people struggle with this topic probably more than anything else? It's not because of the calculus. Because if you look at this, if I gave you just problems like this, differentiate x squared minus 16x. Wait, is there another part to this? Like there's no chain rule, product rule? Most of these problems you don't need the chain rule or product rule. There will be some though. Right? Because we're increasing in complexity. All right? People have problems setting up the equations, but that's algebra and geometry, a lot of geometry in this as well. Right. 8 and negative 8, product is negative 64, difference is 16. 8 minus negative 8 is 8 plus 8, which is 16. Okay. 4 and 5 are introductory type problems. Right? They're not problems that you see on an AP level test. Right. Number 31. That is an extremely common type of introductory problem. It's almost always phrased the same way. The farmer fencing in the pasture. Okay. Also on an introductory type level. Right. The secondary equation here is the perimeter. Basically, think about if you were a farmer and you had a farmhand who did all your menial tasks like mucking the stalls and stuff. That means shoveling the waste matters out. I say, what do I have to do today, boss? You're going to build a pasture. Okay, here's 320 feet of fence. Make it as big as possible. Okay, you wind up being a square, 80 feet by 80 feet. The common follow-up is instead of having the pasture out away from the barn, you got to herd everything in the pasture. Basically, you can think of it as put the pasture right next to the barn so that the animals can go in and out of the barn. So we're going to make the simplifying assumption that the barn wall is long enough as it needs to be. But we should be able to wind up with a bigger pasture because we only need to put fence on 3 sides instead of 2 sides. So primary equation is still the same because it's still the area of a rectangle, which could wind up being a square as it did in part A. The secondary equation is different because you only have fence on 3 sides. All right? So when you find, basically winds up doubling the area because you have 2 80-foot by 80-foot squares next to each other. Okay, same amount of fence, twice as much area. So it makes sense to do that. But you have to be specific about that because if you just say, you have your farmhand, like, hey, I want you to go make a fence 80 by 160. What if the dude goes this way, goes out 160 feet, comes across 80 feet, and then he only has 80 feet of fence left, and then he's got an 80-foot gap here. Like, it's not a real effective pasture, right? You draw him a picture, 80 by 160. So make sure you're clear about which side's parallel to the wall, which side's perpendicular to the wall. All right, for tonight, number 32, work on the curve sketching packets. We're going to have the curve sketching quiz on Monday. Okay, I emailed you another curve sketching packet this morning because I had a request for some extra practice. Okay, take into consideration all those things that I marked up on your packets. All right, they are important because anything that I had to mark up, that's going to be point deductions.